So it has been 1 month. No, it has been 2 months since my last video on the camera project. And as you can see, I've been up to stuff. Last time my camera was still in this wooden case and using this official Raspberry Pi display. And it slots in here. And this worked fine for prototyping, but the issue is that this display is native in portrait orientation and I need it in landscape, and that is annoying to switch around. Well, annoying, it's more like it is not really possible to rotate the camera feed 90 degrees with any hardware acceleration on this platform. Which means I had to switch over to another display. And since my old case was pretty much defined by the size of the old screen, I had to redesign that entirely too. For this iteration of the case, I switched over to a 3D printed design instead. This is mainly just to give me a lot more flexibility with designing how everything will fit together. And it fits together like this. This is my current prototype. And it is significantly smaller than the old wooden box, and you might be able to see I switched a few other things in design, like giving it a micro four thirds mount and this new display. This is now the WaveShare 5-inch display. It is basically the same size as the old one, but it does not have a super wide edge around it. This is also pretty much the most compact version of the camera case I could make with the current hardware in there. Mostly limited by the size of the Raspberry Pi, of course. But as you can see here, the current progress is a lot in 3D printing lens mounts. This is mainly because I wanted to mess around with different sensors for this, but also different lenses, because I've been using these cheap lenses and they work, they are not great. So I needed something better to test the sensors with. And it also needed to be something consistent, because not all the sensors I'm testing have the same lens mounts on it. And if I compare different sensors with different lenses, then it's very hard to actually check the results. Especially because a lot of the sensors you can get for a Raspberry Pi have the lenses built in, like this module. And to properly compare this to the other lenses, to the other sensors, I will have to remove the lens from this to have a bare sensor and then replace it with a lens mount, so I can use the same lens on all the sensors for comparing. As an example of all the different lenses for these cameras, I have some random pieces of lens mounts that have come from other sensors I've been testing, like this basically circular friction fit lens mount that has screw holes that fit some of my sensors but doesn't fit all of them. And it's pretty hard to get anything that actually has consistent mounting options. Like, I'd be lucky if I had just have a CS mount on a sensor, but even that is not available for most of the sensors that are available. So the solution is to pick another lens mount, and in my case I picked the micro four thirds mount, the MFT here. And I basically picked this because I already have lenses that fit this mount that I can use for testing. In fact, I'm using one of the micro four thirds mount lenses right now here for recording. It is quite different to mount an MFT lens than a C-mount lens I've been using. If I grab this C-mount lens, for example, it is just simply threaded. If I get any 3D printed thread that is the same pitch and diameter for this, it should just screw in and it will work. 3D printing a mount for this works reasonably well. I have not actually tried making the camera side for this. I have printed this, which is an adapter from C-mount to MFT, and the threads that are printed here just screw into one of the C-mount lens adapters I have, and it works absolutely fine. But the micro four thirds mount is quite different. If I grab the Blackmagic pocket camera here. This is the smallest camera I have with an MFT mount. You can see it's quite different. It is not a mount that screws in, but it is a bayonet lens mount. So I just need to align these red dots and then it just clicks in. It's very obvious why the world moved from screw mount lenses to bayonet mount lenses. It's just a lot more convenient. It is harder to 3D print though, because the tolerances are way tighter and this locking mechanism is not easy to replicate. There's actually a whole locking pin and spring mechanism behind this, and there is also a spring disc below the lens that actually makes sure that everything stays into place. I realize though that I don't have to print a fully functional Micro Four Thirds mount to mount the lenses, because there's a thing called lens adapters. I have an MFT to F adapter here, and the barrier is an MFT mount, and if I click this into the camera, and I have to align this properly. Now I can fit a Nikon F-mount lens on front of this and it would just work. There's also another special variation of this called an extension tube, which is an adapter that has the same mount on the front and on the back. And in my experience, those are the cheapest ones to get. I have an MFT extension tube right here, and this is one with electronic contacts because I want that for further testing later. And this one does not have the MFT mount on this side anymore because I already took it off, because that is what is on my test 3D prints. The original use of these things is you mount this on a lens and then you put it on the camera, and because this makes the distance between the camera and the lens slightly larger, you change the flange distance, which makes the closest focus point of the lens closer. And also make sure you cannot focus to infinity anymore. But so yeah, it's a trade-off. This is the 3D print I have the mount from that extension tube on. And that is just screwed into place. Let me get a screwdriver. I just reused these 4 screws that came with the original lens mount, and I don't know what the real size of the screws is, so it just screws directly into 3D print instead of using a metal insert. But so far it has worked fine. So I have the front ring here, and below it this is the spring disc. I have no clue what the official name of these parts are, but this one is important. It clamps the lens tightly to the metal ring in front so that the distances of the whole optical system are consistent. So the 3D printed part of this is pretty easy, but making the metal parts I have here, this is the hard part. These parts have by far the tightest tolerances of the entire system, and the spring disc needs to be springy in exactly the right way to make the lens fit correctly. Which is why I decided to not 3D print these parts, but instead harvest them from extension adapters. But the lens mounts are not the only 3D printed parts of this, there's also the cases themselves. After the wooden case prototype, I moved to making a simple rectangular plastic case with a 3D printer just to hold all the parts together. And that worked surprisingly well. I've gone through a lot of iterations of this. I think this is the first one. And this should be the front part that matches it. And, well, this has a FOSS logo on the front of it. And this is the part that is supposed to hold the lens. And the gray part is the one that holds the display and the Raspberry Pi. And these should mount together with 4 screws like this. The first few iterations of these cases didn't actually work together with the lens mounts I designed. Instead, I just have the 4 screw holes and the sensor board from Raspberry Pi Foundation just screw into this and it fits. And it uses, it just has a hole here and it uses one of the original lens mounts. Let me grab one. So here I have the mount from a Raspberry Pi HQ camera, the CS mount, and this is designed to slot into here, and it's normally mounted to the sensor board itself, which holds it into place, and then on the front it just barely exposes the CS mount thread so I can screw in a lens. And this is all just to make it look like it's actually a system that is designed together instead of just some modules screwed into place. I think the green case I have here is the first iteration that has the interchangeable lens mount. All other parts are pretty much the same as the first iteration of the case, and I can just fit one of my lens mount 3D prints in here. And I printed several of these mounts just to get all the distances correct. And this worked great for testing. But this is the first iteration of this lens mount. Because after messing around with this, I figured that I need a larger mounting hole to fit the larger sensor boards. Because I did this design with the IMX 290 I have here. And as you can see, it is slightly smaller than the Raspberry Pi Foundation PCB. And I made the hole for the lens mount not large enough to actually fit the PCB through. As you can see on this prototype, I had to cut away some of the 3D printed case because otherwise I could not fit the Raspberry Pi HQ sensor in here. I had easily enough margin on the front of the lens mount to fit the sensor board, but I had these circular mounting things in the green case that just got into the way of the dimensions of the Raspberry Pi HQ board. If I fit it in here, you can see that it just hits the corners there. So I didn't want to make the mounting hole smaller, so I actually redesigned it so make the whole lens mount a few millimeters larger, so that I have a bit more margin of error for when I find other sensor boards that might be slightly larger. This is the second revision of this sensor board. If I hold them together, you can see it's just the same, just slightly larger. And that's all that needed to make everything fit. And so far I've been trying this with the IMX 290 and the HQ sensor, and it works absolutely fine. But that's not the only prototype I've been working on. This is a completely different kind of design for the camera, which instead of making it look like a DSLR, this actually makes it a box camera. But using the exact same lens mount, so I can exchange parts between these two prototypes. Just like the sensor side, this is the display side, and it is exactly matching the display dimensions of the other printed design. And I can just grab the display module from here and screw it into the side of this camera, and then I have a slightly larger, easy to prototype with case to try things. Let me take this one apart so I can actually show you how this all fits together. This case, the frame of this case is actually the thing I had in my original design blog post, where I thought about maybe having the frame of the camera machined with metal, and then I can have 3D printed sides like this one for prototyping different displays, sensors and that stuff. So this should now be able to be taken out, yes. And this is just a simple bracket that fits with the display module. And just by unscrewing parts I can just easily swap out 5 of the sides of this case to test different things. Like the I/O plate I have on the back. Here's the rear of the camera. This is just a prototype I/O plate I printed quickly. Let's get it in focus first. This currently has a Blackmagic Design SDI converter in here. And the rest I filled up with these Nutric D-ring mounts, or D-mount rings. I never know what the proper name for them is. But you can get a lot of different connectors for them. I have a HDMI one here, and it should be able to just fit in here. And that gives me the HDMI output for the camera. Actually, this covers the text. It should probably be from the rear. Yes, this makes it fit properly. So that gives me the main HDMI output for this camera. And I have 3 more of these holes here for... I have not actually planned it out perfectly. That's why they have no labels on this case. One of them will probably be a USB one, so I can supply power to the camera. And then 2 for audio inputs, which will be 2 XLR plugs. Now, most likely you wouldn't need SDI in your situation. You could just print a new backplate that does not have this SDI stuff in here and swap it out with one that has the exact I/O you need for your situation. So, nicely modular camera. The plan is also to make the electronics for the camera that I will design fit both in this case and in this case. It will be slightly challenging, but not too hard. Basically, the same PCBs that are sandwiched together in this case will be mounted to the sides of the box camera, thanks to these nice flexible cables between everything. So that gives me the flexibility to design it this way. So let's put one of these cameras together. The small one also has a tripod mount on the bottom here, so I can screw in a tripod. It is very convenient for testing because due to the shape, if I put a lens on it, it will just fall over. So I just need a random lens and it should just snap in here like it's an actual camera I bought. And the nice thing about having a standardized interchangeable lenses, I can use any of the lenses I already have for testing the camera. For example, I can switch out this lens for one of the macro lenses I have. And that just works. But this one has some electronics controls for parts of it, so it's not super convenient. What I've actually been using a lot for testing is these Meike Cine lenses. They are a bit heavy, but they are fully manual, and these are ridiculously sharp, which is quite important if you put a small sensor behind it. And even with this lens, which is I think half a kilo, everything seems to hold together fine, even when I don't have all the screws mounted in this case because I was in a hurry. I don't only want to have a Micro Four Thirds mount on here, of course. It just was convenient because I have the lenses, but I also want to make a 3D printed lens mount that can fit the C-mount lenses I have. And that should be these two, because they're just so much cheaper and it should work well enough for most cases. But in this case I just need to figure out the correct lens distance to use for this and then try to 3D print some threading and see if it actually will screw in nicely and stay in place. But I found another interesting lens to mess around with. And I have the prototype right here. Let me try to get that in focus. Yes. So this is an electronic lens I found on AliExpress. It is, I think it's the same zoom range as my C-mount lens. This is an 8 to 50 millimeter lens. And the small one is, it should be on here somewhere, 5 to 50. So this one is actually slightly wider, which means that this one can zoom out more to get a wider shot. This one is also smaller than my other C-mount lenses because this one is designed to cover only a small sensor instead of the potential 1-inch sensor for a C-mount camera. But the most interesting part about this one is that it is hooked up to a breadboard because it has electronics in it. There's, if I zoom in on this a bit, there is 2 motors on the bottom of the lens here, and these are connected mechanically to the focus mechanism and the zoom mechanism in this lens. And with this I have the ability to control those things remotely. And in the case of the electronic focus, it is probably possible to hook this up to the lip camera autofocus code to actually make a camera that focuses itself. My initial prototype I did with this board. This is a quad channel H-bridge breakout board. And this is the most crude way to drive a stepper motor, but it works. But the downside is that this lens sounds like a cheap 3D printer. So on this breadboard I have one of the stepper motor controllers that is very popular in 3D printers. And in theory this should give it very fast and silent operation, but I have not been able to get this thing to work at all with the Raspberry Pi. No matter what I do, there's no power here on the lens motor, and also I have not been able to get any communication from the serial port on the driver board to the Raspberry Pi. I even tried swapping them out for another one, because I have bought two of these, because I need one for focus and one for zoom. And yeah, it would be very weird if both of these were shipped broken. But even if I exchange them, they just won't do anything. So that is a puzzle I've been stuck on for a few days now. But if I manage to get this to work, then I can just get this lens and make it fit. Make something 3D printed around this to make it look like it integrates a bit more in the camera, and hide the electronics and the stepper, and then have something that looks nice and has the ability to remotely zoom and focus. But besides all the lens shenanigans, also the sensors are a thing I wanted to try a few things with. Because the Raspberry Pi sensor, this is the Raspberry Pi HQ sensor, which is the IMX477. This is the best one the Raspberry Pi Foundation offers, but there are competitors, of course. There's a few other companies that offer sensors that are compatible with the Raspberry Pi, and this is one you can get from Waveshare, I think. I got this one from AliExpress. And initially I skipped over these sensors because the specs are worse than the HQ sensor. This is a very slightly smaller sensor than the Raspberry Pi one. But this one is a native 1080p sensor, so all the sensor area actually gets used for the video output, so in the end it actually is better. And not only that, the sensor is surprisingly sensitive to low light, so I get way less noise than with my previous prototype. And I got more sensors, of course. The one I currently have in this camera is almost the same. This is the IMX662, which is a direct replacement for the IMX290. It has the same size, resolution, sensor map even mostly, and it just has better low light performance. Here is some test footage of the IMX462. And yeah, it looks pretty well. This is with one of the Micro Four Thirds lenses on it. And due to the small sensor, it's pretty hard to get any depth of field effect. But for recording conferences, that's not very important. And yeah, I think this looks pretty great. Except there is some issues here with the sides being brighter than the middle of the sensor, and that is mainly because I need to disable or fix the lens shading correction code that is running, that is compensating for using shitty tiny lenses on it instead of a proper one. With a bit of more tuning, this should give some excellent image quality actually out of this camera. Image quality is not the only important part for the camera though. I also have been working on the audio side of this. The Raspberry Pi does not actually have an audio input. It does have an audio output, which is debatable in quality. But for recording conferences, you need some good audio. It's probably the most important part actually. Which is why I decided to make a custom board that will fit on top of the Raspberry Pi. That is also why in all the newer prototypes there is this cutout for the audio hardware. And if you look at this one, it also has a hole for it. And that is for the custom board I made that has some XLR connectors that stick out a bit. This is the custom audio board. It's initially designed around the FOSS audio mixer hardware, but I ended up switching around the ADC to one that has input muxing, so I can have multiple inputs. I found a really nice one that has 6 inputs actually, and then I can pick 2 of those and use that as stereo input for the Raspberry Pi. So here's a Raspberry Pi and the audio board, and the audio board just fits on the 40-pin connector. And that gives me 2 XLR inputs. These are inputs that have enough gain for connecting a dynamic microphone. And these are the channel 1 and 2 for the ADC. Then if I soldered this down, this gives me a stereo line input connected to channel 3 and 4 of the ADC. And then to fill it up, there is a microphone here and one over here if I rotate it. These tiny black rectangles are MEMS microphones. I've just thrown them on here as a test and they performed surprisingly well. And that gives me a stereo microphone built into the camera. It doesn't really have the audio quality you'd expect for recording conferences, but it does provide a scratch audio track that you can use for syncing this with other recordings or maybe for ambient audio from the audience. So, and you can see here that the XLRs stick out of the case because I made the case as small as possible. And due to the way it has to be arranged, the XLR connectors always stick out massively above the Raspberry Pi. It's just a prototype. I will be replacing that with another audio board that has the connectors not soldered on top of it, but the connectors connected to the case instead. But I haven't gotten around to actually designing the details of that part yet. In the last few months I also been working on lots of small fixes and improvements on the firmware of this thing. It has gained a lot of new features, like I have actual white balance controls in here now, as you can see on this picture. And extra monitoring tools like the histogram here, which has been very useful to making sure that the test footage actually looks correct. Also the settings page has been expanded because it now needed controls for the audio. So here the gains for the 2 audio inputs can be selected and the routing on the ADC chip can be changed to select which input you want to use for which channel of the recording. Sadly, the Raspberry Pi hardware seems to be limited to having a stereo input, so you can only ever pick 2 of the 6 channels to record. It would be great if we can figure out a solution for that in the future, but it's not a deal breaker. It's the exact same limitation a lot of the professional cameras have. Other stuff I've been working on is the sensor calibration, because I'm changing the optics of these sensors significantly enough that they need to be changed. So this is a utility I've been working on that uses OpenCV to detect when you hold up a color calibration chart, and then it will do the proper auto white balancing and exposure correction to get a correct raw shot of the sensor of the exact lighting conditions here. And it also connects to a colorimeter over USB to get an exact reading of the color spectrum of the light that is hitting the color chart. And with all that data combined, it is possible to create a new color correction for the sensor, which should help correct for all the color casts you get from having different IR filters in there and just using not the optics this stuff was calibrated with. I've also taken the prototype of this camera to the FOSS infrastructure hackathon, just to have a good comparison with the cameras that are actually used for conference recording, and I've also compared it against Blackmagic Design Pocket 4K camera. In this picture you can see from left to right the Pocket 4K camera, one of the camera prototypes without a case, one of the Sony cameras used for recording FOSS, and finally the first prototype I have made that has the Raspberry Pi HQ sensor in it. And this is some of the comparisons we've made with this. And well, the Pocket 4K has the sharpest video, and that is expected since that is recording in 4K, even though this is downscaled to 1080. And the prototype camera is potentially able to get this quality, but it is difficult to get that with these optics. And on this version of the camera, it's still using the sharpening that is on by default in lip camera, which makes it look a lot worse. I initially was not very happy with the image quality from the prototype camera, but compared to the NX100s from Sony that is used for recording FOSS, the image quality is actually better. I mean, there's slight tint and exposure differences here, and with this firmware I did not have white balance control yet, so that's why the prototype camera has a slight blue tint here. But ignoring that, it certainly has the image quality to at least match a Sony NX100, and that is before using the newer sensors than the Raspberry Pi HQ sensor. So I am pretty happy with the results here. So I think this video is long enough already now, with 30 minutes of rambling about random components of the prototype camera. But I hope you've enjoyed watching it and the progress, at least I have. So if you have any suggestions, put them in the comments. If you have a Raspberry Pi and a camera module, clone the code from GitHub, make a copy of the camera and mess with it. Patches welcome. In any case, thanks for watching.